Okay, we are now going to extrapolate just a little bit from our analysis of the magnetic field produced by a charge moving. And so we have the same plane and other parameters listed here, the radii, different places. But this time we're just going to add a little dq. It's called a current element rather than a moving charge. So here we have a current flowing in a wire, and we're taking a differential length. Now n is number of charges per volume. So the differential Q, how much charge is in here with this current moving in this little dl? Well, it's the amount of charge of an individual charge times the number of charges per volume times the volume. So there's our dq. So that's Qn, and volume is cross-sectional area dl. So there's the volume. And this then is just like dq moving at velocity, drift velocity in the wire itself. So that's really what it is. All right, now we have the magnetic field produced by this dq that has the same geometry as it did previously with the single moving charge. And let's compute then the differential magnetic field, dB, because we're going to get a dB from dq, yes? So we have mu 0 over 4 pi. Now, instead of q, we have dq. And then we have vd, that's the velocity, sine of phi, over r squared. Now, strictly speaking, for this vector, I really should have r caret, or the unit vector, multiplied by this. All right, so the dq is charge n a dl, as we discovered. And then we have vd, sine of phi, over r squared. But now, this looks kind of nasty. Let's see if we can simplify this. Well, what's current? Current is number of charges per volume times amount of charge times drift velocity times cross-sectional area. So that simplifies this a lot as this expression, IDL sine of phi over r squared. So we have differential magnetic field, mu 0 over 4 pi, IDL cross r over r squared, which is the Biot Savart law. Biot Savart. And this expresses the magnetic field due to a current element at some location r at this space, in this spatial direction. Now, our actual circuit then produces magnetic fields from all the differential current elements. And when you consider the magnetic field produced by an entire loop of current, a complete circuit, we then, of course, have to integrate this effect. So we have dB. We need to integrate all the integral of all the dBs, differential Bs, at that location. So the Biot Savart law is generalized then and put into specific form in this way, integral of IDL cross r over r squared. You will, on occasion, have opportunity to use this fundamental equation for magnetic field to discover the actual magnetic field at some location. So when all else fails and right-hand rules and memorized formulas fail, this will give you the actual magnetic field at a location from currents in space and in time. I'm going to rather quickly go through the derivation of the magnetic field from a finite line of current. As you recall from past analyses, the finite situation is usually a little more complex than the infinite consideration, and the one where the wire is infinitely long in the context of the problem at hand, which is actually fairly practical, like as always referred to in electronics or computer circuits, for instance. Those are the ones that are most useful for our purposes, for our problem solving. So we'll cover the basic idea and then get to the result we're really interested in. So we have a current element here, differential length, and we're going to figure out what is the B field. Well, really, the B field produced by this line of current at location P. So here's our DL, and we have r squared of x squared plus y squared, spatial direction, unit vector r. dl cross r, what direction is that? So swing the dl into r, and your thumb points into the page. So the magnetic field produced by this little this differential current, this current element, is into the page here. That is going to be the direction of the B field collectively, because they're all doing the same thing, all the little DIs. Now, the sine of phi equals sine of pi minus phi. So here we have phi. So if you take this 180, basically minus this angle, we get, this angle. So the sine of this angle is opposite, which is x over hypotenuse, square root of x squared plus y squared. So there's sine of the angle. So B, Biot Savart law, mu 0 over 4 pi, I dl sine of phi over r squared. And the I is constant here in this length, 2a. And so it's going to come out, and we're integrating from minus a to a, 1 over r squared sine of phi dy. All right. So here's the B then, where r squared is x squared plus y squared, and there's sine of the angle, so that's kind of messy. And that comes together as 3/2 here, power in the denominator. We look up the tables to see how this works, and we get that the B field is mu 0 I over 4 pi times this expression here. Now that is for a finite line of current. Now as a goes to infinity, here's the part that is going to be useful to memorize. As a goes to infinity, then of course x in this radical becomes negligible, and we get mu 0 I over 4 pi 2a over ax. A's go away, and we get mu 0 I over 2 pi x. Well, that's a lot simpler, isn't it? The B field then is mu 0 I over 2 pi r, where r is the distance from that line of current to some point. So this is very useful. What is the magnetic field produced by a line of current? If we just ask that question, the assumption is that the point in question is reasonably close enough to that wire so that the wire looks like an infinite current. And this is the expression you get for the B field at that location. Well, now we know a little bit about the magnetic field produced by lines of current, and we already knew about the forces on current in a magnetic field. So let's consider a couple examples of the forces associated with lines of current and their interaction with each other. First of all, the B field of two straight parallel current carrying conductors at a long distance away. Now this is just going to be conceptual here. The analysis is a little more involved. I'm not going to derive it all, just kind of give you the result. But to notice that of two parallel conductors, current flowing out, current flowing in, producing their quote-unquote circular magnetic fields, notice they're modified by each other. So the fields are modified. And so the magnetic field externally is perhaps not so simple. Well, separated by distance d. You'll notice in between the two, the magnetic fields strengthen each other. Outside, on either side, if you add up the vector components, you'll notice that they oppose each other. So I wonder if the relationship to R is going to be inverse like it was before with a single conductor. Well, the total magnetic field is actually not. It's an inverse square law. This is what it is without analyzing. Again, conceptually here. The magnetic field is diminished more rapidly because of the oppositely directed B field from the other one over on this side. So it diminishes it faster. But the more they're separated, the less that negative effect is. So the greater the distance d, the greater the B field will be over here. So notice the total B field is proportional to d, in fact, and its inverse square. So this is for r much greater than d. But now more specifically important for our purposes, the force between parallel current carrying conductors. So we're going to consider two conductors separated by R, D or R in this case. So we have a length, we have current 1, and we have current 2. We'll have the currents going in the same direction in this case. The magnetic fields produced around the respective conductors is shown. So the B field at conductor 1, here's conductor 1, we're going to focus on it first, from the current in 2. The current in number 2 produces this B field. Notice out at conductor 2, it's coming out of the screen. So there it is, out of the screen. The magnetic field from current carrying conductor number 2 at number 1. So there's a magnetic field at that location, and it's mu 0 I2 over 2 pi r. That magnetic field now is the field that this current finds itself in, and so there's going to be a force, an IL cross B force. Well, everything is perpendicular, so that makes it easy. So there's the force. Okay, again, put your fingers out of the screen, thumb in the direction of current, I1, palm is pointing down. Likewise, at current number 2, there's the B field. Okay, looking from the geometry of the magnetic field around current carrying conductor 1. And so the force also, in this case, is toward the other conductor, but that means up. So they're trying to come together. They're attracting each other. They're pushed toward each other. That force then is ILB. So here it is. The cross product is complete. So ILB, I1LB, in the B field of current 2. So that B field is this. So multiply it by this quantity, and we get mu 0 I1 I2 L over 2 pi r. That's for parallel conductors. And you can probably surmise what the nature of the force is going to be if one of the currents is in the other direction. So let's define the ampere. And from the previous expression, we have the force between current carrying conductors. Divide by the length, we have a force per length. Here's mu 0. So the force per length would be this expression, product of the currents. Pi's go away here, it's a little simpler. So let's do an example where the currents are 1 amp. The radius, distance between the wires, and the length of the wire is 1 meter. So two current carrying conductors, 1 amp each, separated by a meter, consider a meter length. The force is given by 2 pi 10 to the negative 7, product of the currents times L over R. When we put I, L, and R all 1, we get a force equal to 2 times 10 to the negative 7 newtons. And now you know the answer to the question I posed in the last slide at the end. If the currents are oppositely directed, then the force is directed outward. You probably knew that. So the answer to the question is, how do we define an ampere? If two 1 meter segments of wire separated by a meter have a force of this many 2 times 10 to the negative 7 newtons interacting between them, that is associated with a current of exactly 1 ampere. So just change the current until you get that force, and you got your answer. That's an amp. And now superconductors. Lastly, why are there such large forces in superconductors? Which you may not have known, but there actually is. Consider a solenoid. Superconductor, you can put an arbitrarily large amount of current through. So you get these huge currents, and since it's circulating around, that means the currents are parallel, which means the wires are trying to come together. So we have huge compressional stress. In addition to that, if you take a cross-sectional view and look end to end, we got these massive circulating currents, and the current on one side is opposite the other, which means it's trying to push away from each other, producing large tensile stress. The limitations for humans producing huge magnetic fields is simply the material and mechanics aspect of this. You can keep increasing the current until the force between these is so large that nothing we can do can contain those forces, and the resulting device truly becomes a bomb. And it is very destructive in its potential. And attempts to produce really large, mega Tesla magnetic fields fail because the engineering effort to contain those forces eventually breaks down, and you better take cover, because when that comes apart, the room is probably destroyed as well as the device.